here we have a block accelerating because it's being pushed on by an external force of 80 newtons and it's experiencing kinetic friction. I prefer to just get that out of the paragraph so it's easy to see up here. And what we want in part A is the magnitude of the friction force. So we're going to need the normal force for that. And the normal force is not mg in this case because I have a component downward from my external force, tampering with the vertical direction. And then in B, we want the slide distance in the next 0.9 seconds. Well, that means we need the acceleration, and then we're going to use kinematics to finish it. So let's just start getting into the force analysis up here. And maybe I'll decide that I need another free body diagram down here just to clarify things. We'll see what happens. So first off, it's a little bit weird to see a force with the head of the force attached to the object. It makes decomposing the force vector look a little strange, so I just wanted to clarify something. Sometimes I'm casual about this, but just wanted to make sure everyone understands. So if this angle is 35, then so is this one. And that means the downward component of this force is going to be at 80 sine 35. So I'm going to go ahead and put that in over here. All right, so some of that force is pushing down, and this is how much? That computes to 45.9 newtons down. All right, of course, part of the force is pointing to the right as well. And I can see just looking at this little right triangle, that's going to be an 80 cosine 35. And that computes to 65.5 newtons. In addition to that external force, I have gravity pulling down. I'm just going to put these in qualitatively and then make a new free body diagram because I'm feeling a bit crowded here. Gravity pulls down. Normal force pushes up. And this thing is sliding to the right, which means the kinetic friction force points to the left, and that would be given by mu k times the normal force. Okay, so let's go ahead and make a new diagram down here just to make some space. And you could use a formal free body diagram if you wanted. That's where you represent the object with a mathematical point, or you can use a box. It doesn't really matter. And I'll start to list all the forces on here and compute some of them while I go. So my force of gravity pointing down, mg, that's 10 kilograms times 9.8 meters per second squared, and that gives me 98 newtons. The normal force, it's so tempting to say the normal force is mg because in so many examples it is, but not in this one because the component of our applied force points down. And I'm going to go ahead and just keep the color on that. So it was like this. And that came out to 45.5 newtons. All right, that means the normal force has to do a little bit more to hold this thing up. And then I have a friction force. Fk is mu k n. And then I have a rightward force causing the acceleration of this thing. And let me be good about my color coding. A rightward force, that was a component, so I made it pink. And that was 65.5 newtons. Okay, then we get into the Newton's second law analysis, and the first order of business is to figure out this normal force. So I'm going to do a vertical analysis, so just my y direction analysis. If I want to be maybe a little bit formal about this, F net equals ma in that direction, and the acceleration is 0 vertically because this object is constrained to this surface. And so my net force in the y direction must be 0. If you like, you could write it this way. All the upward stuff minus the downward stuff. must be equal to 0. Or you can think of it like balancing forces. So all the upward stuff has to be equal to the sum of all the downward stuff. If you have a 0 acceleration in one direction, there's nothing wrong with just saying the forces are balanced. So I get 143.9 out of that. Bigger than mg, because I had an external force tampering with the system. Oops, forgot my units. All right, then I can get the friction force pretty quickly. Fk is mu k times the normal force, and that's 0.25 times 143.9. It gives me 36.0. So here I'm just being informal about significant digits. I'm just keeping 3 of them at every step. All right, so now I've got the friction force pointing to the left. I have the component of the applied force that points to the right. That should allow me to find the net force to the right, which in turn would allow me to find the acceleration. So we're getting into part B now. I look at my x analysis. F net in the x direction is equal to mass times the acceleration in the x direction. F net, if I call the rightward direction positive, is going to be 65.5 newtons, minus the friction force that points to the left, 36.0 newtons. That's going to be equal to the mass of this object, 10 kilograms, times the acceleration. Take the difference on the left and then divide by 10. And I end up with an acceleration of 2.95 AX equals 2.95 meters per second squared. And then I can get into the slide distance. So I'm assuming we're starting from rest here, and if I go back to my problem, yeah, we're starting from rest. So I have an acceleration of 2.95. I'm going to call the initial position 0, and then we're going to find some final position x out of this. So x naught is equal to 0. V naught is equal to 0. The acceleration is 2.95. And the amount of time that goes by is 0.9 seconds. So I'll go ahead and write down the first kinematics equation. X naught is 0, V naught is 0, and I've already solved for x final, so all I have to do is plug in. And I've got my slide distance. So that comes out to 1.19 meters.